In previous videos, we've discussed vector addition and subtraction, as well as scalar multiplication. So the next logical step in the development of vector algebra would be vector multiplication. That is an operation that takes two vectors, multiplies them together, and produces something meaningful. If we look at how scalar multiplication and vector addition were defined, they were both defined in the most logical way possible. We just add or scalar multiply in each component. And so one might suspect that if I had a vector u1, u2, u3, and I wanted to multiply this, I'm going to use kind of a star symbol for this, multiply this with the vector v1, v2, v3, a logical result from whatever vector multiplication might be, we might think, well, it's just going to be u1 times v1, u2 times v2, and u3 times v3. So logically this says that we can just multiply the numbers in each component of the two vectors. And while this is certainly an allowable thing to do, there's nothing here that prevents us from doing this. This particular operation has no usefulness. Right? We know that vector addition and scalar multiplication have geometric interpretations, and they have meanings for what those results represent. But in this case, this newly produced vector that we formed by multiplying components together from the two product vectors does not tell us anything. This is just a vector of numbers. It's a perfectly fine vector, but it doesn't tell us anything. And so we'd really like to have a multiplication that gives us something important back. And so it turns out that there's actually two different ways to define a useful multiplication of vectors. And they each will give us a completely different object back, and that object will tell us different things. So the first one, and the one we're going to focus on in this section, is called the dot product. Okay. This one is also sometimes called, in other contexts, a scalar product. And the reason it's called a scalar product is because the result of the dot product of two vectors is going to be a scalar. It's going to be a real number, not a vector. Right? And the other type of product that we're going to talk about in the next section is the cross product. Right? And this will produce another vector. So these are very different types of multiplications. The outputs are different types of objects. But in this section, we're going to focus on dot products. So the first thing we need to do is define how to compute the dot product. Right? So let's say that we're given a vector u, which has components u1, u2, and u3. And another vector v with components v1, v2, and v3. So the dot product which will be denoted u dot v, is given by the following formula. So u dot v is the number we obtain by multiplying u1 and v1 and adding it to the product u2 v2 and adding to that the product u3 v3. Right, so as I mentioned before, this is sometimes called a scalar product because this result is a scalar. This is not a vector. Right? So that that non-useful vector multiplication that I defined in the previous slide, that result was kind of doing the same thing. We multiplied the components together, but then we put it back in vector form. It turns out the useful thing to do is not to put it in vector form, but to then add those components together, like this. Right? The other thing, this is, of course, I define this for vectors in R3. If you had vectors in R2, and you wanted to take the dot product, then you would just forget the U3, V3 term at the end. So the dot product in R2 is this thing in the blue box that I just drew. So we just forget the third component. Right. So let's look at a couple examples. Right. These are, as you can imagine, at least just computing the dot product is pretty straightforward. It's a real number multiplication in addition. Right. So if I have a vector -2, 0, 5, and I want to take the dot product of that with the vector 6, 2, 3. Right? So this is just going to be -2 times 6 plus 0 times 2 plus 5 times 3. And when we compute this out, we get the number 3. Right? It's -12 plus 0 plus 15, and that becomes 3. Okay. To see a quick example in R2, if we had 4, -5, dot 1, 3. Okay, so this would be 4 times 1 plus -5 times 3. All right, so that's -15 plus 4, that's -11. Okay. And I want to do one more just to point out one other thing. Let's take a vector and dot product it with itself. So let's take the dot product of 2, 1, 2 and 2, 1, 2. Right? And so when we do this, we get 2 times 2 plus 1 times 1 plus 2 times 2, which is 9. Okay. Now, the reason I wanted to do this particular one is to then make an observation. And that observation is, if I look at the dot product in kind of its expanded form here, this is just 2 squared plus 1 squared plus 2 squared. Right? So it's just the sum of the squares of the components. And that's something that we've seen before. In fact, if we take the square root of that, then we get the magnitude of the vector. Right? And so this is actually something that will always be true. It had nothing to do with this vector 2, 1, 2. And that is that the dot product is always going to be the square, or I'm sorry, the dot product of a vector with itself will always be the square of the magnitude. So in this case, we see the dot product of 2, 1, 2 with itself is 9, which tells me that the magnitude of that vector is 3, which we could easily compute with the square root. So we know how to compute the dot product of two vectors. So let's look at a few properties that the dot product satisfies. All right, and we will use some of these properties throughout the course as we go through and need to compute dot products in various contexts. So for the purpose of this, let's take 3 vectors, u, v, and w. And these can be in R2 or R3, it does not matter. And I want A to be just a scalar, a real number. Right? So the properties that this product has, it is commutative. So u dot v is equal to v dot u. So we can take the dot product in any order. It is distributive. So if I take u dot a sum, like v plus w, this will be the same thing as first taking the dot product of u and v, and then adding that to the dot product of u and w. Now, one thing to be a little careful about here with this particular property, all three dots do mean dot product, but the two addition symbols here mean different things. So, for example, on the left side here, we have this addition of two vectors, v plus w. That means vector addition. But over on the right side, I have the addition sign here. And remember that u dot v and u dot w are actually real numbers. So over here, this addition is not vector addition, but rather real number addition. So while that doesn't make a difference in terms of how this plays out, a lot of times when we have problems with vectors, we have to keep in mind what's a vector and what is a scalar. And otherwise, we sometimes make some really silly mistakes where we might add a vector and a scalar together or something like that. All right, so just kind of keep your eyes out for that as we go through. Another property of vectors is that if I take the 0 vector and I dot product that with any vector v, right, we will get the 0 scalar. Right? Notice I'm not putting an arrow over that 0. That is actually the 0 real number, not the 0 vector. If we have a scalar a and we want to multiply that times a dot product like u dot v, what we can do is do a couple different things. We could first scale u by a and then dot product that with v. Or we could first multiply v by the scalar a and then take the dot product with u. All right, so this one is actually really useful in computations, and we're going to actually do an example of this fourth property in a moment, just to see how it can be used to help simplify calculations instead of just going straight forward sort of through the order of operations. But the last property is the one we kind of saw at the end of the last example. If I have a vector u and I take the dot product with itself, we're going to get the square of the magnitude of that vector. Right? And this is a really useful property that we'll use in a few different other contexts to help simplify some calculations. So keep in mind that the dot product of a vector in itself or with itself is the square of the magnitude. So to illustrate how these properties, how one of these properties can be used to help simplify a computation, let's say we had a vector u, right, which we're going to define to be 2i plus 3j minus 5k. And I have a vector v defined by 2/3 I plus 2/7 j minus 2k. Right, so I have these two vectors, and I want to compute 21 times u dot v. Right, so I want to take the dot product of these two vectors and then multiply that result by 21. So when you go to compute the dot product, it's not difficult, but you have to be a little careful because there are fractions involved. We'd have 2 times 2/3, we have 3 times 2/7, and then a whole number, -5 times -2. We'd have to add all them together and then add 21. But if we look at vector v and we notice that the denominators of those fractions are 3 and 7, and I have this nice constant of 21, one of the properties of the dot product says I can rewrite this as u dot 21v. So I can scale v by a factor of 21 before I compute the dot product. And so this becomes u which maybe I'll rewrite in component form to save some space. So this is 2, 3, negative 5. That's just copying u down in component form. And then the dot product with 21v, I'm going to multiply each component of v by 21. So 21 times 2/3 will be 14. 21 times 2/7 will be 6. And 21 times negative 2 will be negative 42. Right, so this is just u in component form, and this is 21v. Right, and then the dot product is very easy to do. 2 times 14 is 28. 3 times 6 is 18. Negative 5 times negative 42 is positive 210. And 28 plus 18 plus 210 is 256. Right, so this dot product is 256. Right, of course, if you did the dot product of u and v as originally written, you would end up with a fraction that you would then multiply by 21 to get 256, and that's okay. But this way, we can do a little bit of rearranging at the beginning using the properties of the dot product, and then have a much easier computational part of this particular example.